Good afternoon, and welcome to Managing Mid-Spatial Frequency, or MSF errors for optical surfaces. I'm Jessica DeGroot-Nelson from Optics, and today I'm going to do a whirlwind tour of mid-spatial frequency errors. First, what are mid-spatial frequency errors? What causes them on the surfaces of optics? How are you going to measure them? How can I specify my optics so that my surfaces are smooth? And can you eliminate or reduce mid-spatial frequency errors? We're gonna answer a lot of those questions today, at least touch the surface of them. Let's start and get going. So what are mid-spatial frequency errors? And so mid-spatial frequency errors are periodic ripples that can degrade image quality. These ripple or waviness is defined as a residual periodic undulations on the surface profile. So here's an example of a pretty bad surface with a lot of mid-spatial frequency errors. And you can see in a spiral pattern across the surface. And these, as we'll talk about throughout the talk today, these are caused by sub-aperture polishing techniques. But what they can do to your surface is they can really impact your image quality. And so this is a really good example from Tony Hall in a paper he wrote in 2012. And you can see that the difference of how mid-spatial frequency error impacts the image, and it causes blur in your image quality. And so this is obviously not very desirable. And so we're going to talk about ways to work around this. Before we get going a little bit farther, I want to talk about one other definition, and it's power spectral density, or PSD definition. And what this is a squared magnitude of the Fourier transform of the residual surface height along one dimension of the surface profile. If you take a simplified example, we can use a sinusoidal profile, so a sine wave. If you take the PSD of the sine wave, you're going to get a spike at 1/d, where d is the distance from peak to peak for your sinusoidal profile. But most optical surfaces don't have this straight sinusoidal profile. They're much more randomized. They have a lot of different spatial frequency content in there. And so if we take on the other side here, the ground surface profile and polished surfaces have very similar types of PSD plots. And what you have here is more of a line that indicates that there's a lot of different spatial frequency content on the surface. You can also think of a PSD plot and different points on the PSD plot that correspond to different spatial frequency patterns on the surface. And so if we look at another example on the right-hand side here of a PSD plot, we have power spectral density plotted as a function of spatial frequency or spatial wavelength, which is inverse spatial frequency. So if you want to think of this in terms of length, or the distance between peak to peak of your patterns, you can think of it that way as well. And so you have your waveform, you have your low spatial frequency, these are your form errors. This would be indicated here on your PSD plot. Then you have what we call a lot of times mid, so a little bit finer features would be indicated here. Then your RMS, your roughness, which is your high spatial frequency here. And so the reason I'm introducing power spectral density, or PSD, is that it can be a very useful tool to help visualize mid-spatial frequency errors. So this is a great plot an example that was introduced first by Jim Harvey and then reintroduced by Dave Akins. And so it's a really great tool for helping to visualize these mid-spatial frequency errors. And so when you're looking at a PSD plot, and I've mentioned the terms figure and finish already, is that you see your low spatial frequency, which is what we normally would think of as your irregularity. You have your surface finish, which we think of as your surface texture. And then what's in the middle, your mid-spatial frequency error. So where are these cutoffs, and how can we talk about these a little bit more? So first, your figure. It's the range of spatial frequencies addressable with a simple Zernike expansion. These are your conventional aberrations. And where that cutoff usually will fall is about 5 to 10 cycles per aperture. And then we have, on the right-hand side, we have our finish. Also, sometimes people refer to this as texture or gloss, roughness, and results in total transmission loss due to scatter, or your wide angle scatter. And so, this cutoff typically happens as a function of your optical design. So you have on one side, your cutoff is 5 to 10 cycles per aperture. And then on the right here, it's a function of wavelength and your optical path length. But in the middle, your mid-spatial frequency error, this is where your small angle scatter is happening or your blur. And the reason I'm introducing this PSD plot like this is because it is unique to each optical design. However, at the same time, many times the features that fall within this mid-spatial frequency region for a lot of your optics that tend to be within that more of your what I call handheld systems between, say, 100 millimeters and 400 millimeters, they typically occur because of sub-aperture tool polishing. So this is an example, a very extreme example of mid-spatial frequency broken up into low, mid, and high spatial frequency regions. And so I mentioned that the mid-spatial frequency, that the region is actually defined by the optical design. However, what causes these? And what causes these mid-spatial frequency errors of the surface of the optic? So I'm going to do another quick aside just to get everyone on the same background here and review traditional optical pitch polishing. The goals of polishing to converge to final specifications, remove all trace of damage, and get a smooth defect-free surface. And one of the nice things about traditional pitch polishing is that you're using pitch or polyurethane pads with your polishing abrasive, which is usually cerium oxide and water slurry. And these pads are either full aperture or nearly full aperture. And so that the patterns they're leaving behind are very long strokes and that don't leave the periodic patterns that we typically associate with mid-spatial frequency errors. And then if you're able to run multiple lenses in a multi-block at the same time, you have even longer strokes, and so that you have even smoother mid-spatial frequency regions. And because these traditional processing methods are still very cost-effective for producing spherical optics, this is often used still today. However, deterministic sub-aperture polishing is where a small tool locally removes material, and this is extremely important as we move into using more A-spheres, off-axis A-spheres, free-forms, and very high precision spheres. And the way that deterministic sub-aperture polishing works is it's a Dewell-based algorithm to locally remove material based on the initial surface metrology and tool influence function. An example of one is, here's an MRF spot here. And you can see it's smaller than the sub-aperture. But one of the great things about deterministic sub-aperture polishing, it has a really great predictable surface form convergence. So you take what the surface looks like before, you can then take your polishing spot and you dwell longer on the high points and go faster over the low points. And after, you get nice surface convergence. You get really great form error. However, some of the drawbacks with deterministic sub-aperture polishing is it may require post-smoothing to minimize mid-spatial frequency errors because it's great at removing those low spatial frequencies, your surface form. It's also leaves really good texture a lot of times, so really good surface roughness, but it's in between region because it has trouble removing its own footprint on the surface. And this footprint can be many different sizes. So it can be a few millimeters for really small for an optic that's a few millimeters, or it could be much bigger for meter-sized objects. So you don't have necessarily the same footprint for every single size optic, and that's why it's also kind of scales with the size of your optic. As well. And these signatures, they can be, if you have a rotationally symmetric optic, it can be a spiral or a spoke pattern, or if you have a non-rotationally symmetric optic, it can be raster polish. If you can just polish back and forth across the optic. And those patterns can look different, but either way, these patterns can influence the image of your optic, of your optical system. So they're obviously not desirable. So how do you measure them? And so what is the recommendation for measuring them? I mentioned I'm going to use this visualization tool a couple of times. As a reminder, the mid-spatial frequency bandwidth is unique to each optical design. Okay, so we've talked about, figure, mid-spatial frequency, finish, and these cutoffs here, they fall in different areas based on your optical design. And the reason I'm mentioning this is because the choice of your instrument is going to depend on which spatial frequencies are of interest to you for your optical design. And every method has a different spatial bandwidth. So this is a very simplified PSD plot showing power spectral densities, function of spatial frequency, very qualitatively put here, showing your coordinate measuring machines, profilometers, non-contact profilometers, UA3P, which is a high precision profilometer, interferometry, deflectometry, and white light interferometry. Not all inclusive, but kind of showing the spectrum of different methods to be able to analyze these. And the reason they're overlapping a lot of ways is that sometimes, depending on the spatial frequency of interest, you may want to use more than one instrument. And so here we take, and I'm going to talk mention off-axis A-spheres and freeforms quite a bit, because that's a lot of where some of this work is really critical. Because you must use deterministic sub-aperture polishing to make them. And so, but the metrology gets even a little bit trickier here, because you don't always have a straight on interferometric shot. So this is where high precision coordinate measuring machines can really come into play, and for measuring some of these surfaces. And they can, with really high point density, you can get really good information on the surface, but it can take a really long time. You can have both tactile, right here it's a low force touch probe, or it can be non-contact as well. But these are great for measuring really challenging and unique geometries. Ideally, you want to use something with some type of interferometric technique. So use piezo interferometry, and this has the same interpretation as the Newton interferometer. However, with the piezo interferometer, with the higher resolution information captured and analyzed by the camera computer, you can get some really great information about your mid-spatial frequency errors. And the surface analysis can be extremely powerful using these. However, one of the drawbacks is you need to really be able to capture information off of a spherical wavefront, or perhaps using a computer-generated hologram. If you have a larger aperture sphere, or an A-sphere, another option might be to use stitching interferometry. And this is where you can take multiple sub-aperture measurements and stitch them together. And this type of technique is able to measure convex, concave, sometimes even flat parts in very high numerical apertures up to full hemispheres. So great, another way to capture really good spatial frequency content, but you have to be able to have a surface that is able to be measured interferometrically. Another method that works extremely well is using fringe reflection deflectometry. And so for those of you who might not be familiar with us, fringe reflection deflectometry is a non-coherent imaging technique that measures the local slope by imaging encoded patterns reflected off the surface. So very simply put, you take an LCD screen that has black and white bars on it, and then you reflect it off of the surface to be tested. So this could be an A-sphere, an off-axis A-sphere, a freeform, and then you capture the image with a camera or some type of sensor, and so you're essentially measuring the local slope. And one of the best things about it is that it is very fast and easy to acquire. It can take minutes to be able to capture that information, and it is really quite accurate for measuring mid-spatial frequency errors. So you may be asking, well, why not just use this to measure your surface form too if it's that easy? Well, unfortunately, this method is pretty calibration intensive, and for the low order errors, it's really difficult to measure relative to fiducials and to get the precision required to really know where those low order errors are. And so right now, the bigger recommendation is to use it in process to be able to measure those mid-spatial frequency errors. And that's where I mentioned sometimes it's very helpful to have multiple different techniques, especially if you're going to start working with very complex geometries. So if you start talking a comparison here of deflectometry, CMM, and UA3P. So if you have a freeform, for example, this is an uncoded freeform mirror that's based on fourth order XY polynomial. And this particular freeform is not able to be measured interferometrically. And so we can use a coordinate measuring machine, or the UA3P, which is an ultra accurate 3D profilometer. However, both of these are single point probe touches. And so in order to get the high resolution information necessary for the mid-spatial frequency region, you have to take a lot of data points. And it's possible, but it can be very lengthy. And so this is showing information of comparing the deflectometry, which is a 1-minute acquisition time, versus the CMM or the UA3P, which is a 100-minute acquisition time. So one of the things that you can do moving forward is perhaps lower your point density for your coordinate measuring machine, or UA3P, in order to get your overall form error, and then combine it with deflectometry to get that mid-spatial frequency error. And you can see a very good correlation of looking at mid-spatial frequency between the deflectometry, CMM, and the even higher resolution UA3P. So what do we do to specify them? What should you communicate to a fabricator to specify your surfaces? So again, a reminder, the mid-spatial frequency bandwidth is unique to each optical design. And so this is where the designer needs to be able to communicate, well, what's important to you in order to make sure that you have the highest performing optic in the end. And I've mentioned PSD several times. And so why not do that? So why not just use PSD as a specification? And it's a great tool. It's really good for visualization, but specifying surfaces can be tricky with PSD. It's really important to make sure that there's a commonly used algorithm for analyzing PSD. And then the other thing is it can be very difficult, as many technicians often don't necessarily think in Fourier space. They're used to looking at the optic, both in a false color surface image and looking at fringes, but then and correlating that to what they need to do to be able to correct the surface. But a very nice introduction to be able to capture that information, that spatial frequency content, is to be able to correlate that to your RMS roughness specification, because RMS is proportional to the square root of the area of power spectral density. And it's a function of the spatial frequency limit, which is why I mentioned band limited RMS. So giving an RMS surface roughness specifically for the spatial bandwidth of interest. You can see an example here as a PSD plot as a function of spatial frequency, and you can see the corresponding RMS roughness is different depending on the area under the curve. And so that's where it's important to indicate what are those spatial frequency limits. And this is very important. And then the other thing is dovetails back into how is a surface going to be measured? And so because this is, again, are you going to be measured interferometrically? Is it going to have to be done on a coordinate measuring machine? Are you going to incorporate deflectometry information? These are all things that are very important of how it's going to be measured, and to enable to make sure the instrument that's going to be used, it gets captures the entire spatial frequency region of interest. Another way to specify an optic is using slope. It can pinpoint unwanted features or patterns on the surface. A slope is, back as we remembered in grade school, is rise over run. It's the difference between the heights of 2 points on the surface divided by the distance between those 2 points. It's expressed in angular units, and a complete slope specification contains the slope specification in angular units, either in peak or RMS. A lot of times the default is RMS. Integration length. The default guideline for this is 4% of your clear aperture. So it would be based on the overall size, because as I mentioned, the tool will scale as dependent of if you have a really small optic or really large optic. And so your integration length will help pinpoint that. And then again, the spatial bandwidth. What spatial frequencies are you interested in looking at in your surface? And so your integration length, I want to spend just a second explaining a little bit more about this. It corresponds to the unwanted feature size. And so you can have a longer integration length if you're concerned about large features, or you can go smaller and smaller. But note that as you go to a smaller and smaller integration length, all of your slopes across the surface are going to look a lot larger because you're looking at them over our smaller integration lengths. So we have all of them, the 4 different integration lengths put on top of one another, you can see as you go to shorter and shorter integration lengths, the slope gets higher and higher, the local slope gets higher and higher. But what you want to do when choosing an integration length and a slope specification is think about, well, what is that periodic pattern going to look like on my surface? I want to, what pattern I don't want, and anything larger than that or more extreme than that, that's what you're going to pinpoint here. So here is the green one being repeated across the surface. And so this would be the feature size we don't want. If we were to use the same angle with different integration lengths, you can see that you would, by adjusting your integration length, you're going to be adjusting to get rid of different features on the surface. And one of the things to note is that many times these features are caused by sub-aperture tools. And so for in the region between 100 millimeters and about 400 millimeters, a recommendation or guideline would be to utilize a 1 to 2 millimeter integration length when trying to pinpoint sub-aperture polishing tool marks. Or you can also default to the 4% of the clear aperture, which gives you a pretty good guideline as well. So if you look at an example of slope, so we see the pitch polished surface on the left versus a sub-aperture polished surface, and we take the slope, which is essentially a derivative of the surface. You can see with the pitch polished surface, as you would expect with the full aperture coverage, your slope error is mostly around the edges due to edge effects. Whereas with a sub-aperture rotationally polished optic, you're ending up with features that follow the tool around the surface. So back to that visualization, another reminder. Figure is typically addressed by low spatial frequency errors and Zernike polynomials. Sub-aperture polishers are really good at removing that surface figure. And you can see this evident in this example here is if we use another tool using the Zernike residual R mask to really look at mid-spatial frequency errors. So again, the same example, our pitch polished part versus our sub-aperture rotationally polished part. Pitch polished part still has a lot of those low order errors that are in it. They're dominating versus the sub-aperture rotationally polished part. The mid-spatial frequency errors are dominating because that sub-aperture tool was able to really get rid of the low spatial frequency information. And we can see here that these two parts, the sub-aperture rotationally polished part has 2.5 times lower RMS wavefront error, but has a 3 times higher Zernike residual RMS. So this is another tool to use to really look at mid-spatial frequency errors. So to communicate it on the optical drawing, recommendation is to use ISO 10110 Part 8, which is surface texture, roughness, and waviness. And this is indicated by that square root sign. And you can indicate different specifications using the standard. You can do RMS surface roughness, waviness, RMS surface slope, and power spectral density. There's an excellent reference listed here on the bottom that it contains both a paper and a really good reference poster. And I do highly recommend also purchasing the standard online through the ANSI store, with the website indicated here. So reducing or eliminating mid-spatial frequency errors. One of the best ways to do that is smoothing. So here's an overview of the manufacturing process, going from prescription tolerances of your design, and then you're going to generate the surface, sub-aperture polishing, and then smoothing. You're going to correct and characterize. And then there's also sometimes a loop that happens between sub-aperture polishing and mid-spatial frequency smoothing. And then final metrology and coating. The smoothing step is usually introduced anytime you have a sub-aperture polishing technique in your process. Some of those smoothing methods, there's many of them. There's artisan correction, toolpath algorithms. An example is Zico's pseudo-random toolpaths. Instead of having a raster or rotational polished, a fairly random, so that you don't have those periodic patterns built up. There's also custom tools, slurries. Another example of that is University of Arizona's rigid conformal lap that uses non-Newtonian fluid. Pretty neat stuff. I recommend checking out some of the links here for additional information. And there are a lot of commercial smoothing options available, but many fabricators developed in-house smoothing techniques because it's custom to their processes. An example is going to be presented at OptiFab in 2021 is next generation smoothing using robotic smoothing for freeform optics. This is a platform referred to as Hermes, a high-end responsive mid-spatial frequency elimination system, and developing algorithms for teachable robots or cobots to simulate artisan smoothing. And don't want to steal any thunder, but the preliminary results are showing a lot of promise. So I do recommend checking out this paper. This is an example of a 150 millimeter lightweight ULE sample with a about 3 millimeter phase sheet that's able to remove tool marks from generation, sub-aperture polishing, and then also be able to be a low force or responsive system in order to reduce or eliminate any periodic patterns that can be induced due to quilting of lightweighted an optic. So as we're closing, some of the questions we addressed today: what are mid-spatial frequency errors? They're periodic ripple on the optical surface that can degrade image quality. What causes them? They are caused by optical manufacturing techniques, processes, conditions that leave residual periodic undulations on the surface profile. The worst offender, small tool polishers. How are you going to measure them? Surface profilers, interferometry, and deflectometry. How can I specify my optics that my surfaces are smooth? You can use band-limited RMS, slope, and or PSD specifications, all put on your drawing with ISO 10110 as a guideline. And can you eliminate them? And so, yes, there are many custom and commercial smoothing methods that are integrated into the manufacturing process. And so that I'd like to say thank you very much for joining me for this very much a whirlwind tour. If you have any questions, please feel free to reach out to me directly. My email is listed here. It's jnelson@optimaxsi.com. And I hope you have a fantastic day. Thank you.